Imagine a star so far away, its light has been traveling for 13 billion years longer than the universe has existed to finally reach us, revealing a black hole hidden in the cosmic dark ages. This newly discovered object, a black hole star lurking in the earliest galaxies, could hold the key to unraveling the James Webb Space Telescope's enigmatic little red dot, a faint glow from the universe's infancy that has baffled astronomers. How did such a distant, ancient system form? And why does its light look so strange? This discovery, sitting at the edge of observable space, might finally bridge the gap between theory and observation, shedding light on the first stars, the growth of supermassive black holes, and the very fabric of the cosmos' early evolution. It's not just a record-breaking find, it's a clue buried in time, waiting to rewrite our understanding of how the universe was born. In the vast tapestry of the cosmos, where galaxies stretch across billions of light-years and ancient light from the early universe still reaches our eyes, a new discovery has emerged that could finally unravel one of the most intriguing mysteries of the James Webb Space Telescope. Scientists have identified the farthest black hole star ever observed, a celestial object so distant that its light has traveled over 13 billion years to reach us. This finding, announced in a recent study, is not just a record-breaking achievement in itself, it also holds the key to solving a puzzle that has puzzled astronomers since the first images from the James Webb Space Telescope, JWST, revealed a mysterious red dot in the early universe. Let me explain how this discovery connects to the JWST's little red dot and why it matters for our understanding of the cosmos. To begin, we need to understand what this black hole star actually is. In astronomical terms, a black hole star refers to a star that exists in a binary system with a black hole, a pair of objects orbiting each other, one of which is a massive, collapsed star with such gravity that not even light can escape its pull. These systems are rare but crucial for studying black holes because they allow scientists to observe the effects of a black hole's gravity on its companion star. The newly discovered object, however, is extraordinary. It is the farthest such system ever detected, located in a galaxy that formed just a few 100 million years after the Big Bang. This means its light has traveled through the universe for over 13 billion years, offering a glimpse into the earliest epochs of cosmic history. Now, let's turn to the James Webb Space Telescope's little red dot. When JWST first captured its images of the universe, one of the most striking features was a small, red-hued galaxy that appeared in the background of the iconic early universe image. This galaxy, known as GNZ11, is one of the most distant objects ever observed, with a redshift so high that its light has been stretched into the infrared spectrum. Redshift is a phenomenon caused by the expansion of the universe. As light travels across expanding space, its wavelength stretches, shifting it toward the red end of the spectrum. The higher the redshift, the farther away the object is, and the older the light we're seeing. GNZ11's extreme redshift suggested it was formed just 400 million years after the Big Bang, making it one of the first galaxies to take shape in the universe's history. However, the exact distance and properties of this galaxy have been a subject of debate. While its redshift implies a vast distance, confirming its actual location and characteristics has been challenging due to the limitations of previous telescopes. This is where the discovery of the farthest black hole star comes into play. The new object, which scientists have dubbed a black hole star due to its association with a black hole, is located in a galaxy that is even more distant than GNZ11. By studying this system, astronomers can refine their understanding of how galaxies formed in the early universe and how black holes influenced their development. The key lies in the way light from these distant objects is affected by the universe's expansion. The farther an object is, the more its light is stretched, and the more we can learn about the universe's structure and evolution. However, measuring these distances precisely requires advanced techniques, and the JWST's ability to observe in the infrared spectrum has made this possible. The black hole star discovery provides a critical data point that helps calibrate these measurements, offering a clearer picture of the early universe. To appreciate the significance of this finding, we need to step back and consider how astronomers determine the distances to distant galaxies. One of the primary methods involves using standard candles objects whose intrinsic brightness is known, allowing scientists to calculate their distance based on how bright they appear from Earth. However, in the early universe, such objects are scarce, making distance measurements challenging. The black hole star discovery introduces a new type of standard candle, a binary system where a star's light is distorted by the gravitational pull of a nearby black hole. This distortion, known as gravitational lensing, can provide additional information about the mass and distribution of dark matter in the universe, which in turn affects how light travels through space. By observing these systems, scientists can create more accurate models of the universe's expansion and the distribution of matter, which are essential for interpreting the JWST's observations. The connection between this discovery and the JWST's little red dot lies in the broader context of understanding the early universe. GNZ11's extreme redshift suggests it is one of the first galaxies to form, but its exact properties, such as its size, star formation rate, and composition, have been difficult to determine. The newly discovered black hole star provides a way to test and refine these assumptions. For example, by analyzing the light from this system, scientists can study how black holes interact with their host galaxies and how these interactions might have influenced the formation of the first galaxies. This is particularly important because black holes are thought to play a crucial role in galaxy evolution, regulating star formation and shaping the structure of galaxies through their gravitational influence. Understanding these processes in the early universe could help explain how galaxies like GNZ11 came to be. Another aspect of this discovery is its implications for the James Webb Space Telescope's ability to peer into the early universe. The JWST's infrared capabilities are essential for observing distant galaxies because the light from these objects has been stretched into the infrared spectrum. However, the telescope's instruments must be calibrated to account for the effects of cosmic expansion and the distribution of matter in the universe. The black hole star discovery provides a natural calibration point, allowing scientists to refine their models of how light travels through space and how the universe has expanded over time. This, in turn, improves the accuracy of distance measurements for objects like GNZ11, helping to resolve the mystery of its exact location and properties. Moreover, the discovery highlights the importance of studying binary systems involving black holes. These systems are rare but valuable because they offer a unique opportunity to observe the effects of a black hole's gravity on its companion star. By analyzing the light from these systems, scientists can infer the mass of the black hole, the orbital dynamics of the system, and even the presence of other unseen masses, such as dark matter. The black hole star discovered in this study is particularly significant because it is so far away, meaning its light has traveled through an immense amount of space, potentially revealing information about the universe's structure and evolution that is not accessible through other methods. In summary, the discovery of the farthest black hole star is a milestone in our quest to understand the early universe and the role of black holes in shaping it. By providing a new data point for calibrating distance measurements and refining models of cosmic expansion, this finding helps resolve the mystery of the JWST's little red dot. It also deepens our understanding of how galaxies formed in the first few 100 million years after the Big Bang and how black holes influenced these processes. As we continue to explore the cosmos with instruments like the James Webb Space Telescope, discoveries like this remind us that the universe is still full of surprises, and each new observation brings us closer to unraveling its deepest secrets. In the vast, uncharted expanse of the universe, where light from distant stars takes billions of years to reach our eyes, scientists have long sought answers to some of the most profound mysteries of existence. One such mystery has puzzled astronomers since the James Webb Space Telescope, JWST, first captured its iconic little red dot image, a faint, distant object that defied immediate identification. Now, a groundbreaking discovery has emerged from the depths of space, offering a tantalizing clue to unravel this enigma. At the heart of this revelation is a celestial object so far away that its light has traveled over 13 billion years to reach us, a black hole star, a term that describes a stellar mass black hole surrounded by a luminous accretion disk. This object, the farthest of its kind ever found, has become a focal point in the quest to decode the JWST's mysterious red dot. But how did scientists stumble upon this distant cosmic relic, and what tools and techniques did they employ to confirm its existence? Let's journey through the intricate process that led to this discovery, a testament to human ingenuity and the relentless pursuit of knowledge. The story begins with the James Webb Space Telescope itself, a marvel of engineering and a revolutionary instrument in the field of astronomy. Launched in 2021, JWST was designed to peer deeper into the universe than ever before, thanks to its advanced infrared capabilities. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet wavelengths, JWST can detect light that has been stretched into the infrared due to the universe's expansion. This ability is crucial for studying the earliest galaxies and the formation of stars and black holes, as the light from these ancient objects has been redshifted into the infrared spectrum. However, the JWST's most iconic image, the little red dot, was not immediately recognized as a distant galaxy. Instead, it appeared as a faint, red-hued speck, its origin shrouded in uncertainty. This enigma sparked a cascade of investigations, leading scientists to explore the possibility that the object might be something entirely different, a black hole star. To confirm this hypothesis, researchers turned to a combination of cutting-edge instruments and sophisticated observational techniques. The JWST's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, played pivotal roles in capturing the faint light from this distant object. These instruments are equipped with advanced sensors and adaptive optics, allowing them to detect even the faintest signals from the cosmos. However, the challenge lay in distinguishing this object from other potential sources, such as distant galaxies or foreground stars. To achieve this, scientists employed a technique known as spectroscopy, which involves analyzing the light emitted by an object to determine its composition, temperature, and motion. By breaking down the light into its component wavelengths, researchers could identify unique spectral signatures that would indicate the presence of a black hole star. But the journey to confirm this discovery was not without its hurdles. The object's extreme distance meant that its light was incredibly faint, requiring the JWST to capture data over extended periods. Additionally, the interplay of cosmic dust and gravitational lensing, where the gravity of massive foreground objects bends and amplifies light from distant sources, complicated the analysis. To overcome these challenges, scientists combined JWST's observations with data from other telescopes, including the Atacama Large Millimeter/Sub-Millimeter Array, ALMA, and the Hubble Space Telescope. These collaborations allowed for a more comprehensive analysis, cross-referencing data to eliminate potential false positives and refine the object's properties. A critical breakthrough came when researchers focused on the object's redshift, a phenomenon that occurs as the universe expands, stretching the wavelength of light. By measuring the redshift, scientists could determine the object's distance and age. The JWST's instruments were uniquely suited to this task, as they could detect the subtle shifts in infrared light that indicate extreme distances. The redshift measurement not only confirmed the object's location in the early universe but also provided insights into its environment. For instance, the presence of a massive accretion disk around the black hole suggested that the object was actively feeding on surrounding material, a process that emits intense radiation. This radiation, in turn, could explain the faint but detectable signal captured by the JWST. The confirmation process also involved meticulous data analysis, leveraging machine learning algorithms to sift through vast datasets. These algorithms helped identify patterns and anomalies that might have been overlooked by human observers. By training models on known astronomical data, scientists could predict the likelihood of the object being a black hole star rather than another celestial phenomenon. This approach not only accelerated the analysis but also increased the accuracy of the findings, ensuring that the object's characteristics aligned with theoretical models of black hole behavior. Another key factor in the discovery was the collaborative effort among international teams of astronomers. The JWST's mission is a global endeavor, with contributions from scientists across multiple countries and institutions. This collaboration allowed for the pooling of expertise, resources, and observational data, creating a robust framework for analysis. For example, the team might have included experts in gravitational lensing, who could assess whether the object's light had been amplified by foreground galaxies, or specialists in black hole physics, who could interpret the spectral data in the context of existing theories. Such interdisciplinary cooperation is essential in tackling complex astronomical puzzles, as no single discipline can provide a complete picture of the cosmos. The timeline of this discovery is as remarkable as the object itself. Following the JWST's launch, the telescope underwent a rigorous commissioning phase to calibrate its instruments and test its capabilities. Once operational, the team began a series of targeted observations, focusing on regions of the sky where distant galaxies and potential black hole candidates were expected. The little red dot was identified during one of these surveys, prompting an in-depth investigation. Over the following months, the team refined their observations, adjusting for instrumental limitations and environmental factors that could affect the data. The culmination of these efforts led to the confirmation of the object as a black hole star, a finding that has since sparked further research into its implications. The significance of this discovery extends beyond the immediate mystery of the JWST's red dot. By identifying a black hole star at such a vast distance, scientists have gained valuable insights into the early universe. Black holes are thought to have played a crucial role in the formation of galaxies, and their presence in the early cosmos could shed light on the processes that shape the universe as we know it. Moreover, the detection of such an object highlights the power of modern telescopes to probe the universe's most distant corners, opening new avenues for exploration. The JWST's ability to capture this signal, despite the immense challenges posed by distance and faintness, underscores the technological advancements that have transformed astronomy in recent decades. As we reflect on this journey, it becomes clear that the discovery of the farthest black hole star is more than just a scientific achievement, it is a testament to human curiosity and perseverance. The process of confirming this object involved a blend of cutting-edge technology, collaborative effort, and meticulous analysis, each step revealing new layers of understanding about the universe. The JWST's little red dot mystery, once an enigma, now stands as a beacon of what is possible when we push the boundaries of our knowledge. As scientists continue to explore the cosmos, discoveries like this remind us that the universe is full of secrets waiting to be uncovered, and that every observation brings us one step closer to unraveling the mysteries of existence. Farthest black hole star ever found could help solve the James Webb Space Telescope's little red dot mystery. This part of our deep dive into farthest black hole star ever found could help solve the James Webb Space Telescope's little red dot mystery focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For centuries, humanity has gazed at the night sky, wondering about the mysteries of the cosmos. But it wasn't until the 20th century that we began to unravel some of the most profound secrets of the universe, secrets that would eventually lead to the discovery of black holes. The idea of a black hole, an object so dense that not even light could escape its gravitational pull, was first proposed in the early 1900s by Albert Einstein's theory of general relativity. Einstein's equations suggested that if a massive star collapsed under its own gravity, it could form a region of space where the gravitational field was so intense that nothing, not even light, could escape. However, this was just a theoretical concept, a mathematical curiosity rather than an observed phenomenon. For decades, scientists debated whether such objects could truly exist, or if they were mere artifacts of the equations. The first real evidence for black holes came in the 1960s, when astronomers detected strange X-ray sources in the sky. These sources were too faint to be stars, yet they emitted intense radiation. It turned out that these X-ray emissions were coming from material spiraling into an invisible, supermassive object, what we now call a black hole. The discovery of these X-ray binaries, like the famous Cygnus X1 system, provided the first concrete proof that black holes were real. But even as astronomers confirmed their existence, the question remained: how many black holes are there in the universe, and what roles do they play in the evolution of galaxies? The search for answers led to a series of groundbreaking missions and discoveries over the past few decades. In the 1970s and 1980s, ground-based telescopes and space observatories like the Hubble Space Telescope began to map the distribution of black holes in the cosmos. One of the most significant breakthroughs came in the 1990s with the discovery of quasars, distant, luminous objects powered by supermassive black holes at the centers of young galaxies. These quasars, some of which date back to just a few 100 million years after the Big Bang, provided crucial insights into how black holes might have influenced the formation of galaxies. Yet, despite these advances, the full picture of black holes remained elusive. For example, scientists struggled to understand how supermassive black holes could form so quickly in the early universe, or how smaller stellar mass black holes populated the cosmos. The answer, it turned out, lay in the faint, distant objects that had long been overlooked. Enter the James Webb Space Telescope, launched in 2021. With its unprecedented sensitivity and ability to peer into the early universe, JWST has opened a new window into the cosmos. One of its most intriguing discoveries was a faint, red dot in the sky, a seemingly unremarkable object that defied easy classification. This so-called little red dot puzzled scientists because its properties didn't match those of a typical star or galaxy. Some speculated it might be a distant galaxy, while others thought it could be a black hole. The mystery of this object became a focal point for researchers, as it hinted at the presence of black holes in regions of the universe that had previously been difficult to study. But how did we get to this point? The journey to understand black holes and their role in the universe has been a long and winding path, filled with discoveries that reshaped our understanding of the cosmos. The early 20th century saw the theoretical foundation of black holes laid by Einstein's equations, but it wasn't until the 1960s that observational evidence began to confirm their existence. The discovery of X-ray binaries, such as Cygnus X1, marked a turning point. These systems consist of a normal star orbiting a compact, invisible object, with the star's material being pulled into an accretion disk around the black hole. The intense heat of this disk emits X-rays, allowing astronomers to infer the presence of a black hole. This breakthrough demonstrated that black holes were not just theoretical constructs but real, physical entities. However, the question of how many black holes existed in the universe remained unanswered. The answer, it turned out, was far more complex than anyone had anticipated. In the 1990s and 2000s, astronomers began to realize that black holes come in different sizes. Stellar mass black holes, formed from the remnants of massive stars, were one thing, but the discovery of supermassive black holes at the centers of galaxies posed a new puzzle. These objects, millions or even billions of times more massive than the Sun, were found in the nuclei of galaxies like our own Milky Way. The challenge was understanding how such massive black holes could form so quickly in the early universe. Some theories suggested they formed from the direct collapse of massive gas clouds, while others proposed that they grew by merging with smaller black holes. These ideas laid the groundwork for future discoveries, but they also highlighted the gaps in our knowledge. The next major leap came with the launch of the Hubble Space Telescope in 1990. Hubble's ability to capture high-resolution images of distant galaxies allowed astronomers to study the distribution of black holes in greater detail. By observing the motion of stars around galactic centers, scientists could estimate the mass of supermassive black holes. These observations confirmed that supermassive black holes were common in the universe, with nearly every large galaxy hosting one at its core. However, Hubble's capabilities were limited by its sensitivity to visible light, which meant it couldn't detect the faintest or most distant black holes. This limitation set the stage for the next generation of telescopes, including the James Webb Space Telescope. JWST's infrared capabilities allowed it to peer through the dust and gas that obscured distant objects, revealing structures and phenomena that were previously hidden. One of the most significant discoveries made by JWST was the detection of a faint, red dot in the sky, a mysterious object that defied easy classification. This object, which scientists dubbed the Little Red, was so distant that its light had traveled billions of years to reach us. Its properties were unlike those of a typical star or galaxy, leading to speculation that it might be a black hole. But how could a black hole appear as a faint, red dot? The answer lies in the nature of black holes and the way they interact with their surroundings. When a black hole accretes material, it heats up the surrounding gas, emitting radiation that can be detected by telescopes. However, if the black hole is surrounded by a thick cloud of dust and gas, its emissions might be obscured, making it appear faint or even invisible.
This phenomenon could explain the little red dot mystery.
But the significance of this discovery goes beyond just solving a single puzzle. It highlights the importance of studying black holes in the early universe, as these objects may have played a crucial role in shaping the cosmos.
By understanding how black holes formed and evolved, scientists can gain insights into the processes that governed the universe's development.
The discovery of the little red dot also underscores the limitations of previous telescopes and the transformative power of JWST. While Hubble and other observatories had provided valuable insights, they couldn't detect the faintest or most distant black holes. JWST's ability to observe in the infrared spectrum allows it to peer into regions of the universe that were previously inaccessible, revealing new phenomena and challenging existing theories. This newfound capability has opened the door to a new era of discovery, one where the mysteries of the cosmos can be explored with unprecedented precision. The journey to understand black holes and their role in the universe has been a long and complex one, marked by theoretical predictions, observational breakthroughs, and technological advancements. From Einstein's equations to the first X-ray binaries. From quasars to supermassive black holes, each discovery has built upon the last, bringing us closer to understanding the full scope of the universe. The little red dot mystery is just one piece of this larger puzzle, but it represents a significant step forward in our quest to unravel the cosmos. As scientists continue to analyze data from JWST and other observatories, they are uncovering new insights that challenge existing theories and expand our knowledge of the universe. The farthest black hole star ever found, which may be linked to this mysterious red dot, could provide critical clues about the nature of black holes and their role in the evolution of galaxies. This discovery is not just a milestone in astronomy, it is a testament to humanity's enduring curiosity and our ability to look beyond the known to explore the unknown. The discovery of the farthest black hole star ever found has opened a new chapter in our understanding of the universe, but it has also raised more questions than answers. This object, which is actually a quasar powered by a supermassive black hole, lies at the edge of the observable cosmos, its light having traveled over 13 billion years to reach us.
Its existence challenges our current models of how such massive black holes could form so early in the universe's history.
But its significance goes beyond its own peculiarities. It may hold the key to unraveling a mystery that has captivated scientists since the James Webb Space Telescope first captured its iconic little red dot image. This enigmatic glow, which defied expectations, has sparked debates about the nature of the early universe, the role of dark matter, and the processes that shaped the first galaxies.
Yet, despite the excitement, many questions remain unresolved, and the answers may lie in the very extremes of cosmic evolution.
The little red dot, a term that has become synonymous with the first image captured by the James Webb Space Telescope, was a revelation. At first glance, it seemed like a simple, distant galaxy, but its brightness and color were far from ordinary. The dot's red hue suggested it was extremely distant, and its intensity hinted at something unusual, a massive, luminous object emitting vast amounts of energy. Scientists were puzzled. How could such a bright object exist so far away, and what did it tell us about the universe's infancy? The quasar discovered recently, which is even farther than the little red dot, may provide some answers. But it also raises new mysteries. For instance, how could a supermassive black hole, which typically takes billions of years to grow, have formed so quickly in a universe that was only a few 100 million years old? This question is at the heart of the debate surrounding the early universe and the formation of the first galaxies. Quasars are among the most luminous objects in the universe, powered by supermassive black holes that accrete matter at an astonishing rate. The one recently discovered is so distant that its light has been traveling for over 13 billion years, meaning we are seeing it as it existed just a few 100 million years after the Big Bang. This places it in the era when the first galaxies were forming, a time when the universe was still young and its structure was in flux. The sheer brightness of this quasar suggests that its black hole was already massive, which is perplexing. According to current theories, black holes grow gradually through the accretion of gas and mergers with other black holes. However, the existence of such a massive black hole so early in the universe's history challenges these models. It implies that either the processes of black hole growth were much more rapid than previously thought, or that there were other mechanisms at play that allowed for the formation of these giants in the early cosmos. Scientists are still grappling with these possibilities, and the discovery of this quasar has only deepened the mystery.
One of the leading hypotheses is that the quasar's black hole formed through a different mechanism than the ones we observe today.
Some researchers suggest that the first black holes may have been seeded by primordial gas clouds or dark matter halos, allowing them to grow rapidly in the early universe. Others propose that the quasar's brightness is a result of its extreme environment, where the surrounding gas and dust are so dense that they fuel the black hole's accretion at an unprecedented rate. However, these ideas are still speculative, and there is no consensus on which mechanism is responsible.
The quasar's discovery has also raised questions about the role of dark matter in the formation of the first galaxies.
If dark matter played a significant role in the early universe, it could have influenced the distribution of gas and the formation of massive black holes. Yet, the exact nature of this interaction remains unclear, and further observations are needed to determine its significance. The connection between this quasar and the little red dot mystery is not just a coincidence. Both objects are extreme examples of luminous, distant galaxies that defy conventional expectations. The little red dot was so bright that it suggested the presence of a massive, energetic source, and the newly discovered quasar may be a similar phenomenon. However, while the little red dot was a single, isolated object, the quasar is part of a larger system, with its own host galaxy and surrounding environment. This distinction highlights the complexity of interpreting such distant objects. The little red dot may have been a rare, extreme case, while the quasar represents a more common phenomenon that we have yet to fully understand. By studying these objects together, scientists hope to piece together a more complete picture of how the universe evolved in its earliest stages. Despite the excitement surrounding these discoveries, there are still many unresolved questions.
For example, how do we reconcile the existence of such massive black holes with the timeline of cosmic evolution? Current models of galaxy formation suggest that supermassive black holes grow over billions of years, but the quasar's discovery suggests that this process may have been much faster in the early universe.
This has led to a re-evaluation of the role of feedback mechanisms, such as radiation from the black hole itself, in regulating star formation and galaxy growth.
If the quasar's black hole was emitting so much energy, it could have influenced its surroundings in ways that we have yet to quantify.
However, the exact impact of these processes remains uncertain, and more data is needed to refine our understanding.
Another mystery is the relationship between the quasar and its host galaxy.
In many cases, quasars are found in massive, mature galaxies, but the quasar discovered recently appears to be associated with a galaxy that is still in its infancy.
This suggests that the processes driving quasar activity may be different in the early universe. It also raises questions about the interplay between black hole growth and galaxy evolution. In the modern universe, there is a tight correlation between the mass of a galaxy's central black hole and the properties of its host galaxy. However, the quasar's discovery implies that this relationship may have been different in the early cosmos, and understanding this could provide insights into the broader evolution of galaxies and their central black holes. The implications of these discoveries extend beyond the study of black holes and quasars. They also have profound consequences for our understanding of the universe's structure and the role of dark matter. If massive black holes formed so quickly in the early universe, it could mean that dark matter played a more significant role in the formation of the first galaxies than previously thought. This would challenge existing theories about the distribution and behavior of dark matter, which is still one of the greatest mysteries in cosmology. Additionally, the extreme conditions in quasars may provide clues about the nature of the early universe, including the formation of the first stars and the distribution of gas in the intergalactic medium. However, these connections are still speculative, and further observations are needed to confirm them. As scientists continue to study these distant objects, they are also facing the challenge of interpreting the data they have already collected. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, has allowed us to peer further into the universe than ever before. However, the data it provides is often complex and requires sophisticated analysis. For example, the light from these distant objects is stretched due to the expansion of the universe, making it difficult to determine their exact properties. Additionally, the presence of intervening gas and dust can distort the light, complicating efforts to study the objects directly. These challenges mean that even with the latest technology,
there is still a lot we do not yet understand about the early universe and the processes that shaped it. In the end, the discovery of the farthest black hole star and its potential connection to the little red dot mystery represents both a breakthrough and a puzzle. It has given us new insights into the formation of supermassive black holes and the evolution of the early universe, but it has also highlighted the gaps in our knowledge. The scientific community is still debating the mechanisms behind these phenomena, and the answers may require new theories, observations, and even technological advancements.
As we continue to explore the cosmos, these mysteries will undoubtedly shape the next chapter in our understanding of the universe.
For now, the journey continues, driven by curiosity, the pursuit of knowledge, and the enduring quest to uncover the secrets of the cosmos. Farthest black hole star ever found could help solve the James Webb Space Telescope's little red dot mystery. This part of our deep dive into farthest black hole star ever found could help solve the James Webb Space Telescope's little red dot mystery focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. So there it is, the farthest black hole star ever found, a cosmic beacon from the early universe, and it might just hold the key to solving one of the James Webb Space Telescope's most puzzling mysteries.
Let me break it down.
First, this object, identified as a quasar powered by a supermassive black hole, is so distant that its light has traveled over 13 billion years to reach us.
That places it just 300 million years after the Big Bang, a time when the universe was still young and its first galaxies were forming. Now, the JWST's little red dot mystery refers to a strange glow detected in the earliest light of the universe, light that seems too bright for its distance. Scientists have been scratching their heads because, according to current models, such light shouldn't exist. But here's the twist: this newly discovered quasar might be the missing piece. Its intense brightness, combined with its extreme distance, could explain the red dot as a natural phenomenon rather than an anomaly. It's like finding a flashlight in a dark room when you thought the power was out. But wait, there's more. This discovery isn't just about solving a puzzle, it's about rewriting our understanding of how black holes and galaxies evolved. These quasars, once thought to be rare in the early universe, might have been far more common than we believed. If they were widespread, their collective light could have played a crucial role in shaping the cosmos, illuminating the first stars and galaxies. The JWST's data, combined with observations from other telescopes, is helping us piece together this story. By studying these distant quasars, we're not just looking back in time, we're tracing the roots of the universe's structure. But how did we even find this object? It took a combination of advanced imaging, precise measurements, and a dash of luck. The JWST's infrared capabilities allowed astronomers to peer through the cosmic haze, revealing light that's been stretched and dimmed by the universe's expansion. This quasar's light, though faint, was bright enough to stand out against the backdrop of the early universe. And its position in the sky, along with its spectral signature, confirmed it was a black hole-powered engine churning out energy at unimaginable scales. This isn't just a discovery, it's a breakthrough. It challenges existing theories about the growth of supermassive black holes and the timeline of galaxy formation. If these quasars were common in the early universe, it suggests that black holes grew rapidly, possibly fueled by collisions between galaxies or streams of gas.
But there's still much to learn.
The red dot mystery isn't fully solved yet.
While this quasar offers a compelling explanation, scientists are still analyzing its data to confirm its role. Other factors, like the distribution of dark matter or the behavior of primordial gas, might also play a part. What's clear is that this discovery is a stepping stone. It shows how the JWST's capabilities are revolutionizing our view of the cosmos, revealing secrets that were once hidden behind the veil of time.
For astronomers, this is a reminder that the universe is full of surprises. Every new observation brings fresh questions, and every answer opens new doors.
The journey to understand the cosmos is far from over, but with tools like the JWST, we're getting closer than ever. So, if you've been wondering what the little red dot really is, now you know it's part of a larger story, one that's still being written. And if you're curious about how this discovery fits into the bigger picture of the universe's origins, you're in the right place.
FactVerse is here to take you on daily deep dives into the mysteries of space, science, and the unknown.
Subscribe to stay updated, and if you have your own theories or questions about this discovery, drop them in the comments.
The universe is full of secrets, and we're just beginning to unravel them.